Now that we've started talking about trees, you'd think that I would be excited to introduce a few data structures based on trees, which obviously I am, but we're not going to do that in this lecture. The first big application of trees that I want to cover is actually a theoretical one. It's a way of using trees as a formal device. In fact, I want to revisit comparison sorting. Now that we know enough about trees, I will be able to use something called a decision tree to prove a result about comparison sorting algorithms that is incredibly profound. So the first thing I have to do is tell you what a decision tree is. Let's take a look at this simple algorithm on the left. It's called min2, and its job is to find the minimum of two provided things, A and B. And it does this by means of a comparison operation. And a decision tree is a conceptual way to represent some decision process, some sequence of decisions, including, for example, the decisions made by evaluating the result of comparison operations. Now, I've referred to comparisons twice now. Maybe you can see where I'm going with this. And I think the best way to sort of understand intuitively what a decision tree is just to look at examples. I feel like the diagrams that we draw of decision trees are rather natural, whereas providing you some formal explanation, to be honest, actually makes them harder to understand to some extent. So we need the formal definition, but it's easier just to look at a few of them to get a feel for what decision trees are. And so a decision tree corresponds to some decision sequence with a variety of different outcomes. And each outcome is something that you come to based on the decisions that you made, based on a series of questions that were asked and the results of those questions. So for the time being, let's just look at this very simple model to get a feel for the syntax of what a decision tree is, and then I'll show a more complicated one in a minute, and we can talk about the different ways that we can traverse a decision tree. So the internal nodes of the decision tree correspond to questions, effectively, for our purposes. And for today, they're just going to be yes or no questions. Although you could think about a decision process where the questions you ask at each step could have multiple outcomes, that more than two of them, for example. That would be valid, but for our purposes, because we care so much about these true or false comparison operations, we're going to limit ourselves to yes or no questions, to these basically true or false comparisons. Although other types of operations could show up that have binary results. The advantage of doing this is it means that the tree we end up with, if every internal node corresponds to a yes or no question, and the children of each internal node correspond to the different possible outcomes of that single question, what that means is that we're guaranteed to end up with a binary tree. That's a big deal because we can employ things that we know about binary trees to get the result that we want. And then the leaves of my decision tree correspond to outcomes of the complete decision sequence. So while the children of an internal node correspond to the different outcomes of the question posed by that node, once I get all the way to the bottom of the tree, so in this case, of course, the tree just has height 1. There's only one question I'm asking. But notice that if I ask the question, is A less than B, and the answer comes back yes, then I can conclude that the minimum is A. Actually, a little side note here. Throughout this lecture when I talk about comparisons, I am making the assumption that we've made all along that in the event that A and B are equal, then both of them count as the minimum, so it doesn't really matter which one I return in that case. In this case, I think I return B. If A is less than B, I return A. Otherwise, including the case where they're equal, I return B. But keep that in mind. I don't talk too much about the case where various things are equal in these discussions of minimum algorithms, but that's because in the event that there are two elements tied to be the minimum, either of them is viable as the minimum. And so the leaves of the decision tree correspond to the overall outcome of my decision process. And in cases where you're solving a problem where you need to ask a series of questions or use a decision process to get to your result, or you can argue a decision process must be embedded in what you're doing, we could use the decision tree to reason about the way an algorithm works. Another thing I'm going to observe is that this decision tree captures all possible paths of execution. It doesn't make any difference what values you plug in for A and B. This decision tree models the decision process. And that's a key point. Now, it's going to turn out later, as we work with algorithms which have a variable input size, because this algorithm's input size is fixed, there's only ever going to be two input values. When we work with algorithms that have a variable input size, the decision tree structure will change based on the size of the input, but not based on its contents. So if I work with an algorithm that takes an array as its input, then the decision tree corresponding to the case where the input has size 10 will be different than the decision tree for the input of size 15, for example. But if I consider any input of size 10, there is one decision tree that covers all the possible paths of execution for any input of size 10. So here's a decision tree for min3, so an algorithm to compute the minimum of 3 values. And for this one, let's do a quick example. So suppose I have 3 values, and the idea behind this decision tree, as I said a minute ago, is it captures the decision process needed for any collection of 3 inputs, no matter what they are. So let's choose, let's make the minimum in this one C. Okay, so B is 17, and C equals 6. Okay, so let's follow the decision process that the min3 algorithm uses to decide which of these 3 things is the minimum. Okay, so the first question it asks, and in general, the way the decision process is modeled, is that the root of the decision tree corresponds to the first question you ask, the first decision that you have to make. And in a sense, that's why it branches out, because at the beginning, there's only one question you're going to ask every single time. But based on the result of the first question, you might ask a different second question. Okay, so we begin at the root of the decision tree and we ask the question, is A less than B? Okay, well, A is 10 and B is 17, which means that the answer is yes. So we go to the left. Okay, we now ask the question, is A less than C? Okay, well, A is not less than C because A is 10 and C is 6. So A is not less than C, so the answer is no. And that means we return C. And sure enough, C is the minimum. Now, one thing that we should clarify here is that the decision tree doesn't capture every aspect of the algorithm's behavior. So an algorithm that, I don't know, loops over the elements of an array or adds up a bunch of stuff, well, some of that isn't a decision process, and that wouldn't be captured in a decision tree. But we know that when we're performing some task that requires making a lot of decisions, for example, deciding which element is the smallest requires using a bunch of comparison questions, we can use the decision tree to model that aspect of the algorithm. The actual goal of this lecture is to talk about the minimum number of operations needed by a comparison sorting algorithm. And we know that comparison sorting algorithms do all sorts of stuff that isn't, comparing 2 elements together. So they might copy elements, they might rearrange them, and that's fine. If I want to talk about the minimum number of operations of a comparison sorting algorithm, and I can show that the comparison sorting algorithm has to perform, maybe this number of comparisons, well, of course, that means the algorithm must take at least this amount of time. So although the decision tree doesn't capture everything about the algorithm, it does capture one pretty important, pretty salient detail about algorithms that are based on decision processes, like comparison sorting algorithms. So anyway, as I said a minute ago, each internal node of my decision tree corresponds to a single comparison, and the children course, or in general the paths away from that node, correspond to the different outcomes of that question and the decision of what to ask next. And as I said, because we're only working with yes or no questions in this lecture, that means our decision tree is guaranteed to be a binary tree. And then the leaves of the tree correspond to the outcome of the process. So they're not comparisons, they are the conclusion that I can draw after a sequence of different decisions, after a sequence of asking different questions. Notice that there's no requirement in general that the different outcomes be unique. That is, we can see there actually are 2 paths that lead us to return C, because in the way I wrote this algorithm, I return C in 2 distinct places, because I can reach that conclusion in a variety of ways. And you could write your own min3 algorithm that has a completely different decision tree, and that's fine. A decision tree corresponds to a specific algorithm. My goal at the end of this lecture is to make a general statement about all decision trees that are possible for comparison sorting algorithms. So anyway, as I said, we're only going to consider cases where the decision tree is a binary tree. The reason we like that is because that allows us to apply theorems we know about binary trees to decision trees. It's perfectly valid because there are questions one could ask with multiple outcomes. It's perfectly valid to think about decision trees in general having more than 2 children per node or having an arbitrary number of children per node. It's just that we're not going to need to do that for our purposes. So, as I said, decision trees don't capture all of the work required by the algorithm, just the behavior of conditional branching, or in general, the behavior of the decision process underlying the algorithm. There are some algorithms I could write that don't really make any decisions at all. They just perform some repetitive task. And of course, for those, decision trees don't tell us very much. But because in a comparison sorting algorithm, the only way that the algorithm can learn about its input is by asking questions of this form, it is reasonable to assume that a decent amount of the algorithm's running time is consumed by asking questions. And so what I'm going to do is use the fact that the decision tree of any comparison sorting algorithm has certain properties to make a general, very broad statement about how many operations every comparison sorting algorithm must perform in the worst case. And so basically what I'm going to do going forward is I'm going to attempt to assert that the decision tree for comparison sorting algorithms has a particular height. And we know that because the decision process consists of starting at the root and working our way down the tree, it's possible that the leaves of the tree are at different depths. But if there's any leaf at a particular depth, there has to be some way for the decision process to reach that leaf. And that means that we could argue there must be some input to my sorting algorithm that takes me all the way to that leaf of the sorting of the decision tree for the sorting algorithm. So if I can assert that the decision tree for a particular algorithm has height h, then we can bound the minimum number of operations needed by the algorithm on a worst case input. And again, the idea there is that because if I have to walk through 2 internal nodes to get to a leaf, performing the comparison for each internal node requires at least one operation, right? Which means it does take at least that number, big theta of h, operations to perform the decision process. Let's take a look at an algorithm that isn't just finding the minimum of things. Let's take a look at linear search. Now, inside of the linear search function, you can see there are some things going on that aren't modeled in this decision tree. In fact, there are even likely some comparison operations that I've chosen to exclude from my decision process that I've chosen to model. So I've modeled the decision process only as it applies to the elements of my array. Arguably, some sort of comparison is probably happening to evaluate the loop condition, and it's not relevant to me because all that would do is make the decision tree larger. I want to make an argument about the minimum number of operations needed, so I'm free to throw operations away in my analysis because I can still assert that the number of operations is greater than or equal to the number that I end up with. So for linear search, I could think about the decision process like this. So linear search, in this example, and the one we've been working with all along, returns the index at which it finds the first occurrence of some value k, which means at each step, if it ever comes back with the answer yes on any of the questions it asks, then we've immediately reached an outcome. And so the decision tree, as a result, has leaves at different levels. So I begin by asking the question, is A0 equal to k? And if the answer is yes, well then the value k occurs at index 0, so I'm done. And you can see I immediately reach an outcome. If the answer is no, I walk down and I ask, okay, is A1 equal to k? And that's done through some algorithmic machinery, but it doesn't make much of a difference to me from the tree point of view. Exactly how I do that, I mean, I could do this recursively, for example. Exactly how I do that is sort of irrelevant. The decision process is the same. So I ask, is A1 equal to k? If the answer is yes, then I return 1, otherwise I keep going. And eventually, if nothing is equal to k, I sort of bottom out and I hit this -1, return -1 at the bottom, and then that's the last outcome. So in certain cases, I can argue that it is necessary to get all the way down to this leaf, and that requires 4 comparisons, which of course it requires at least 4 units of time. I could also argue that if I try to imagine the decision tree I would get if I expanded this out to some arbitrary size n, that it would look pretty similar to this, and therefore it's reasonable to argue that linear search would require at least n operations on some array, on an array that brought me all the way to the return -1 case. We already proved a lower bound on searching in general, and so we know that, of course, searching an unsorted array requires at least n operations. But I want to be careful here. I am going to prove a lower bound in this lecture, but what I just described as far as linear search is concerned, if I were to prove a lower bound by saying, oh, the decision tree for this linear search has depth n, and you might or has height n, and you might actually have to walk all the way down to the last level to get to an outcome, that may be true, and I could prove that, but it would only apply to this particular linear search function. I couldn't make a broad statement about all searching because some searching algorithms don't have a decision tree that looks like this. So anyway, what we also can reason, and we'll come back to this later, is regardless of how you write your search function, if it's a search function designed in this methodology where you return the index where you find something or you return -1, well, there are n possible indices you could possibly return because n possible places for the value k to show up, and one other thing, -1. So there are n plus 1 possible outcomes. And that's true whether I'm using this implementation of linear search or any other, because the problem requires that. In any specification of the problem where you return an index of the array if the element is found or -1 otherwise, there are n plus 1 possible outcomes. So regardless of how you assess those outcomes, exactly how you ask whether the value is in a particular index of A and what order you do that, there need to be at least n plus 1 leaves of my decision tree. That is a statement I can make about all unsorted array searching algorithms in general. And I intend to do something similar for sorting. So that's where I'm going with this. I don't know what the decision tree for a particular algorithm looks like, and so it's hard to make broad statements about decision trees of all possible algorithms because, what about all the algorithms that haven't been invented yet? But I can draw some conclusions about certain things that must apply to all decision trees by reasoning about the problem. For example, a decision tree for an unsorted search problem needs to have at least n+1 leaves. It could have more than that because we've already seen that a particular outcome can occur in more than one leaf, but it needs to have at least n+1 leaves. Now, let's begin talking about decision trees for sorting algorithms. And in this section, I'm going to represent the leaves, the possible outcomes, in a sort of condensed notation. And so right at the outset, I want to talk about that condensed notation. Let's do an example. So let's consider a 3-element sequence. This particular decision tree corresponds to sorting 3 different elements. And so it's the decision tree for the decision process involved in comparison sorting. And as I mentioned earlier, we know that the only way a comparison sorting algorithm can learn about its input, can distinguish one input from another one, is by using comparisons. It doesn't know anything else about the values in the input array besides what it learns from comparisons. And that's one of the reasons why what I'm talking about today doesn't really apply to non-comparison based sorting algorithms. It doesn't apply to radix sort or bucket sort. We've already seen that radix sort and bucket sort can finish all the way through without ever comparing one element to another. So this only applies to comparison sorting algorithms where we have that really strict assumption that we can make that the only way they can distinguish between different inputs is via comparisons. Before I do the example, I want to get to the slide where the example is supposed to show up. So as I said a minute ago, we are only able to use this model and have it and be assured that it will hold because we know that comparison sorting algorithms have no other way of understanding their input besides asking these questions. And then we have to observe that it does make sense if I consider comparison sorting on an array of size n, that if I give 2 different arrays, 2 arrays that are in a different order, the algorithm has to be able to tell them apart. Because when it decides to sort the array, when it rearranges elements of the array, the rearrangement it performs has to be different for 2 arrays that are in a different order. It wouldn't make sense to be able to apply the same rearrangement to 2 different arrays and get back the same sorted representation. And so here's where I could do the example. So let's suppose that I'm sorting a 3-element array. So I've got 3 values, A, B, and C. And let's make sure it's not too obvious. So we'll make the sorted representation. So A is 17, B is 6, and C is 10. So the sorted ordering of these is going to be B, then C, then A. And so the outcome of the decision process, after learning about my input, should be that we conclude that this is the sorted ordering. In other words, I should expect to end up at this leaf of my decision tree. But let's try it out on this particular sorting algorithm. So this decision tree is just the decision tree of one possible sorting algorithm. I think it's actually merge sort, and the slides will confirm that in a minute. Okay, so I first asked the question, is B less than C? Okay, so B is 6 and C is 10. So the answer is yes. So I go to the left. Okay, now I ask the question, is A less than B? So A is 17 and B is 6. We can see that it is not less than B, so we go to the right. The answer is no. Now we ask the question, is A less than C? So A is 17 and C is 10, and the answer is no. So we go over here. And that means we can conclude the sorted ordering of my elements is B and then C and then A. So the outcome that I've written in the tree in this condensed notation is simply that at the bottom level of the tree, once I get to this leaf, what I've been able to conclude is that the sorted ordering is B, C, A. And what I want to observe is if I give you this input, so that's the input that I just had corresponds to this array of size 3, then I guess you could argue one way of sorting it would be to rearrange values by moving the 6 to the beginning, moving the 10 to the second position, and moving the 17 to the third position. Okay, now let's consider a different arrangement of the same elements. Let's suppose we've got 10, 6, and 17. What I want to argue, and I think this is very intuitive and obvious once we just say it, is that if I apply the same rearrangement, so the same arrows basically, if I move elements around in the same way, there's no way that this array will be in sorted order if I apply the same rearrangement as the earlier array. But let's do it. Okay, so I move the last element into the second position, I move the second element into the first position, and I move the first element into the last position. And so I get 6, 17, 10, which is obviously not sorted. sorted. And so I think that's a good justification that a sorting algorithm needs to learn enough about its input that it can distinguish between all of the possible arrangements of my array. Okay, so now the question is, how many possible arrangements are there of my array? And strangely, the answer is that there are a finite number, and I mentioned this in the last 2 lectures ago, that it's odd because you think about there being an infinite number of possible arrays of size n, because there's so many different elements you could use, so many different types of data. But ultimately, there are only a certain number of ways they can be arranged. So if my array only has these 3 elements in it, there's 3 elements, which means I can only arrange them in, at most, 3 factorial ways, so 6 different ways. And I can think of other arrays on different elements that are effectively the same as far as sorting is concerned. So for example, what about this array here? 300, 100, 200. And although the elements in the array are different, ultimately their distribution is exactly the same. The largest thing is first, the smallest thing is second, and the thing in the middle is third. So what I can consider is, well, the sorting algorithm doesn't actually care that much that these elements are distinct. It just cares about the relative ordering of elements. And therefore, I'm not going to worry about having distinct, different subsets of elements. I just care instead about the different ways a fixed set of elements could be arranged. So let's consider an array of n elements and consider all the different arrangements that I could pass into a sorting algorithm. So suppose I only want to sort the values 1 through n, for example. And there are lots of different ways of rearranging 1 through n. So I could have 1 and then n and then 2 and then n minus 1 and so on. Or I could have n and then n minus 1 and then n minus 2 and so on. But suppose I just consider, I suppose my input array is just the values 1 through n. Now sorting algorithms in general have to deal with a lot more possible inputs than these, but I'm talking about a lower bound. I want to show the minimum number of operations. And if I can show that sorting algorithms that are restricted to just inputs on these elements require a certain number of operations, that means that the more general sorting algorithms that can sort literally anything have to use at least that number of operations as well. Okay, so an array of n elements may have up to n factorial distinct arrangements. And there's a cryptic note here, and I can justify that just a bit. So let's consider let's consider these arrays here. So 3, 1, 3. Okay, well, if we consider all the possible ways of arranging 3 things, so if my arrays are, if my arrays consist of the elements 1, 2, 3, how many ways are there to rearrange the elements 1, 2, 3? Okay, well, there's 1, 2, 3 itself, then 1, 3, 2, then 2, 1, 3, then 2, 3, 1, then 3, 1, 2, and 3, 2, 1. So there are 6 of them. That's 3 factorial. You can argue, though, that this array here, if I try and rearrange the elements, there really aren't 6 different rearrangements. So I'll put them in order. So I've got 1, 3, 3. Okay, so I could also do 3, 1, 3, or I could do 3, 3, 1. But I don't know that I have any other options because any other rearrangement would just match up with one of the existing ones. So if I only consider cases where all n elements are distinct, then it's reasonable the sorting algorithm, because it has to be able to sort arrays where all of the elements are distinct, could have to deal with up to n factorial possible arrangements. And this decision tree reflects that. So for my arrays of size 3, there are 6 possible permutations of elements, and that means 6 distinct input cases that the sorting algorithm has to distinguish between. And the key thing to observe here is it doesn't make any sense. It would be absurd for me to be able to pass in this array and this array separately to the same sorting algorithm, and for it to assume these are the same array and still sort both of them. It has to be able to tell these 2 permutations apart, or it will never be able to sort both of them. It has to, because they need to be sorted using different sets of operations. So the argument I want to make there, which going forward I'm going to assume is a sort of a settled argument, is that if I'm thinking about the decision tree for a comparison sorting algorithm, where there is a leaf for every possible sorted ordering that I could come up with, there have to be at least n factorial leaves in that decision tree. So the tree above does correspond to merge sort. My earlier hunch was correct. This is the sequence of decisions made by a merge sort implementation on arrays of size 3. Now remember what I said earlier, that the decision tree for n equals 3 corresponds to the path of decisions for every possible input of size 3. If I begin talking about arrays of size 4, there will be a different decision tree for all of the different arrays of size 4. In fact, we'll get a chance to see it near the end of the lecture. And so the decision tree changes based on the size of the input, but not based on the input itself. So if I pass in any array of size 3, there is some path in this decision tree that allows me to figure out out how to sort that array, to conclude what the sorted ordering is. Now, what the algorithm does to actually rearrange the array and put it into the sorted ordering isn't really any of our business. All we're talking about is the number of comparisons needed to figure out what its input array is. So here is the decision tree corresponding to selection sort. Actually, one last word about the merge sort thing. You'll notice on the slides I say the sequence of decisions made by a merge sort implementation. I'm not claiming that every merge sort implementation has exactly this decision tree, because of course you could split the array in different ways. All I'm claiming is I implemented merge sort, and this is the decision tree for my implementation on inputs of size 3. We're only using this as a visual device anyway. So this is the decision tree for my selection sort implementation on arrays of size 3. It's a different tree, but you'll notice that it also has 3 factorial or 6 leaves, because there are 6 different ways the input could be arranged. And I need to distinguish between the 6 different sorted orderings of the input elements. So for example, if you give me these 3 elements, well then the sorted ordering is just leaving them in order. So if A is equal to 6, B is equal to 10, and C is equal to 17, then I get the sorted ordering is just A, B, C. Whereas if I have these 3 elements, 6, 17, and 10, then the sorted ordering would be A followed by C followed by B. If I have these 3 elements where I've got, let's see, this would be 10, and then B is the largest, and then C is the smallest. The sorted ordering is C first, and then A, which is 10, and then B. And so you can see there have to be at least 6 leaves of this decision tree, because there are at least 6 different rearrangements that could be necessary to sort my array. Now let's take a look at the structure of the tree for selection sort, because it shows us some things that maybe hint at why selection sort is slower. Now, there's all sorts of other reasons that sorting algorithms can be slow. Notice that for the merge sort tree, the tree is sort of compact. It does as little work as it possibly can. In fact, if I think about a tree that has 6 leaves, it makes sense it needs to have height at least 2, because there's no way to get 6 leaves with only height 1, because the maximum number of, with only internal nodes up to level 1. Because if my internal nodes are only up to here, then there can only be 4 children. And so to have 6 children, to have 6 leaves, I need to have some internal nodes sitting down at level number 2. But with selection sort, all internal nodes or all leaves are actually at the same level. They're all at the bottom of the tree. And we notice there's these 2 nodes that look a bit weird. They only have 1 child. And what that tells us is that this question wasn't necessary. I don't actually need to ask if B is less than A, because there is only 1 possible answer. So asking the question was a waste of time. And so these you could sort of think of this as a degenerate case. Now, it's still a binary tree because it's valid in a binary tree for a node to only have 1 child. I'm not bothering to draw it as the left or right child, although it is true, I guess, that this, by the convention we're using, this would be the right child and that would be the left one. The key thing is that if there is only 1 leaf, it means there is no path that could ever result in this question having a yes answer. There is no input that would ever result in a yes answer, because the comparison we're performing at that node is redundant. And to illustrate that, let's just take a look at the root let's do the root and the one on the left. So, okay, let's just walk through this. So suppose I ask the first question, is A less than B? And the answer comes back yes. Okay, so things that we know. We now know that A is less than B. I then ask whether A is less than C, and the answer comes back no. So I now know that A is not less than C. And then I ask, is B less than A? And I realize that B can't be less than A because A is less than B. I already know that. So of course the answer is no. The answer can't be anything else. And so selection sort is a bit oblivious here. It's asking a question it doesn't need to know the answer to because the answer is obvious. And that's sort of a hint as to why selection sort is so slow. It's using a decision process that contains all this redundancy. And the same thing's actually happening over here, because we ask if A is less than B, and the answer is no, A is not less than B. And then later, we come down here and ask if B is less than A. And in the event where all 3 of our input values are distinct, then either A is less than B or B is less than A. They're never going to be equal. And even if they were going to be equal, we don't actually care for sorting purposes. If they're both the same, we can leave them in either order. So for the sake of selection sort, if I'm sorting 3 distinct values, like the values 1, 2, and 3, this comparison is also completely useless. And yet selection sort does it anyway. It wastes time doing a comparison it doesn't need to do. And so this is sort of an illustration. It doesn't prove anything for us because it's just a diagram that I drew, but it's an illustration of how selection sort is doing some work it doesn't need to do compared to merge sort. Okay, so what I want to do in this lecture is show that no matter how you design the sorting algorithm, the decision tree you come up with must have a certain height. And because we know that if we only model nodes in our decision tree for outcomes that are possible, that is, I don't bother drawing in the leaves that correspond to impossible outcomes, then it means that every leaf in my decision tree is going to be some valid input. There actually is an input that could get me all the way to that leaf. And if I assume it takes 1 unit of time at least to perform each comparison along the way, I can then make a statement about the minimum number of operations needed by the sorting algorithm in the worst case, no matter what sorting algorithm it is, as long as I can prove something about the way that tree looks. Okay, so the first thing we need is a theorem about the height of the tree related to the number of leaves, because I intend to prove that if the decision tree has n factorial leaves, then it has a certain height, a certain minimum height. And then, okay, so the theorem I'm going to prove is simply that if you have a binary tree with a certain height h, it has at most 2 to the h leaves. And it seems like this is the opposite of what I'm trying to establish. I want to show that if it has a certain number of leaves, it has a certain minimum height. But this theorem is pretty easy to prove, and I can reverse engineer it, I guess, to prove the result I really want to use today. So I wonder how I'll choose to prove this. Well, I mean, there's only really one guess at this point. Obviously, it's going to be induction. And induction on trees is just so wonderful. It just feels so good. So why not? Why not do an induction proof? Okay, so my theorem is a binary tree with height h has at most 2 to the h leaves. As usual, I can leverage the fact that and this is great about induction proofs involving the height of the tree, because when h equals 0, the only possible tree is just one node by itself. And that means that it's really easy to prove things about a node by itself. So the only possible tree is a single node, and that node happens to also be a leaf. The unique case where the root of the tree is the leaf is where you're working with a tree of height 0. So there's one leaf, which is equal to 2 to the 0, and that means that the height, which is 0, there are at most 2 to the 0 leaves. Okay, good. So the theorem holds, we're good. For the hypothesis, suppose that all binary trees with height k have at most 2 to the k leaves for every value k in this range, up to some value h greater than or equal to 0. So it is a stronger hypothesis. I'm not sure if I actually need that here, but it is easier, and in general, stating it isn't that difficult, and so if the proof needs it, it's good just to state the stronger hypothesis. Oh yeah, no, I guess I do need a stronger hypothesis because of this situation. Okay, so here's my induction step. Consider some tree T of height h plus 1. All right, so let's take a look at what T must look like. So T has height h plus 1, so the height is h plus 1, and we know that h is greater than or equal to 0, which means h plus 1 has to be at least equal to 1, and that means that the root of my tree cannot be a leaf. If the height is at least 1, then the root has to have at least one child. Okay, so I've got these two children over here. We'll just draw, in an abstract sense, the two subtrees of my root. I also know that because the height of my tree is h plus 1, the height of each of these subtrees cannot be larger than h. It could be smaller than h. In fact, for all I know, they could be empty, but the subtrees certainly cannot have height h plus 1. The reason why this is nice is that means that because these things have height at most h, I can apply my induction hypothesis. So that's why I needed the stronger hypothesis, because I can't be guaranteed they both have height exactly h. One of them has height h, but the other one could have some other height, but neither of them can have height greater than h. Okay, so because both of the subtrees have height at most h, the induction hypothesis applies, and I can say that each subtree has at most 2 to the h leaves. It could have fewer than that. I guess I'm making the implicit assumption here that if the height is less than h, well then, so suppose the height is 2, well the number of leaves is at most 2 to the 2. But as long as 2 is less than h, then the number of leaves is less than or equal to 2 to the h. So each of my two subtrees has at most 2 to the h leaves. Then the total number of trees in the entire tree, because we know that V is not going to be a leaf. It can't be because it has children. The total number of leaves is just the number in the left plus the number on the right, and that's going to be at most 2 times 2 to the h, which is 2 to the h plus 1, and that proves that the theorem holds for my tree T. Because I chose T to be any binary tree of height h plus 1, this is applicable to every tree of height h plus 1, so I've now shown in my induction step that every tree of height h plus 1, that the theorem holds for every tree of height h plus 1. And therefore, by induction, the theorem holds for all values of h greater than or equal to 0. But that isn't the result I actually need for the purposes of this lecture. What I want to prove is that if you have a certain number of leaves, the height must be at least a certain value. But I can get that. So the theorem I actually want is this. A binary tree with k leaves has height at least equal to h is greater than or equal to log base 2 of k. And the way I get that is I just take the theorem I just wrote and take the logarithm of both sides. So if I have a tree with k leaves and height h, so we know that the largest number of leaves possible in a tree of height h is 2 to the h, which means if my height is h and my number of leaves is k, k has to be less than or equal to 2 to the h. And then I just take the log of both sides, and I get log base 2 of k is less than or equal to h, or in the way I'd prefer to write it, h is greater than or equal to log base 2 of k. Okay, great. That's not really a theorem worth of proof. It's a pretty simple proof, but it's an important enough result that we'll go ahead and call it a theorem anyway. Okay, that's step one on our journey to proving a general result about all comparison sorting algorithms. And I think it's time to finally to sort of spoil the outcome here. This is the theorem that we're going to get to at the end of this lecture. Our main result for today is this theorem, which is saying that any comparison-based sorting algorithm must use at least n log n operations asymptotically in the worst case. Now, of course, it could take more. I mean, you could write a comparison sorting algorithm that took 2 to the n time for all I care, but there is no comparison sorting algorithm for which every input can be sorted in better than n log n time asymptotically. So it's weird to talk about big omega in the worst case, but it's important here because we know that there are sorting algorithms that are somehow able to sort certain inputs in linear time. So insertion sort, for example, can sort certain inputs in linear time. This theorem is simply saying that if you pick any comparison sorting algorithm, there is going to be some input that requires at least n log n time. And this theorem, obviously, is a really big deal because it tells us that if we're going to look for asymptotically optimal sorting algorithms, that we've already found one. There is no way of getting a comparison sorting algorithm that is better than big theta of n log n. And since merge sort is big theta of n log n, that means that merge sort is asymptotically optimal. Now, it's not just merge sort that's in that boat, so there's lots of algorithms, lots of sorting algorithms out there that are big theta of n log n. We even saw last time that we can, or 2 lectures ago, that we can make quicksort run in big theta of n log n time if we're willing to write a hideously complicated version of quicksort. So there are other n log n comparison sorting algorithms. I just like merge sort, so I name drop it here. The key thing is we don't need to worry about finding a faster one. That is as good as we can do asymptotically. We certainly could consider if we could make a more streamlined one that was a bit faster in a constant sense, but we can't get asymptotically better than n log n. So what I want to do in this lecture is to prove this theorem. And we've already seen some bits and pieces of it, but I need to put all the pieces together to write an actual proof of the theorem. And so the way I'm going to do this is I'm going to show that the decision tree for any comparison sorting algorithm has to have height at least this number. And we can see that this number is going to be big omega of n log n. Although if you're skeptical, because we know we can throw away that over 2 there, that's a constant. Whether we can throw away the constant inside the logarithm, maybe you're skeptical about that. I do illustrate that with the algebra when the time comes. So the idea is, because running a comparison sorting algorithm, you can model at least part of the comparison sorting process with a decision tree, because the comparison sorting algorithm has to ask a series of these comparison questions, like is A less than B, in order to figure out what the array looks like. It has to learn enough about the array to be able to distinguish all of the different input orderings from each other. There are at least n factorial different orderings of the input data, and that means that it turns out that the decision tree needs to have n factorial leaves, and we're going to show that that means the decision tree's height is at least this number. Because every input that I feed into my comparison sorting algorithm runs a decision process that's equivalent to traversing the tree from a root to the leaf, if the height of the tree is equal to this, there have to be some inputs that where the outcome, the leaf of the tree, is all the way down at this level, and that means the algorithm requires at least this number of comparisons and that amount of work, and that's big omega of n log n. And of course, if the algorithm performs n log n comparisons, it needs at least n log n running time, because it also does other work as well, and none of that's going to be, negative or anything, so it's definitely going to require at least n log n time. Okay, the way I'm going to do this is I'm going to just break the different parts of my proof, the different stages into small lemmas, and I'm either going to prove or justify them all separately, and then the actual proof of the theorem will just be a few paragraphs at the very end where I just say, here's where I use lemma A, here's where we use lemma B, and so on. Okay, lemma A. The decision tree for any comparison sorting algorithm must have n factorial leaves because there are n factorial different possible sorted orderings. If I know nothing about my input, there are n factorial different rearrangements that could be necessary depending on the properties of the input. Because I've already talked about that at great length in several different ways, we're not going to bother with a formal proof of it. I actually think that to a large extent that is something that follows from the properties of sorting, so I will treat it as self-evident. If you wanted to write a hyperformal full proof of lemma A, what you probably, I guess my best suggestion is what you could do is you could say, let's assume the decision tree has fewer than n factorial leaves. So suppose that there are less than n factorial possible leaves, or suppose that like this was a leaf or something. What you do in that point, in that case, is show that there must be two different arrays that are distinct, that have different orderings. So again, different orderings would be stuff like these two orderings here. These are different orderings. Sorting them requires different rearrangements. If you have fewer than n factorial leaves, there must be two different arrays that are in a different order that the algorithm treats exactly the same way. That is, it has no way of telling them apart because it doesn't ask enough different questions. And if you think back to our lower bound proof from lecture, what was that, lecture 4, I guess, when we talked about searching, it's the same idea as there. If the algorithm can't tell these two arrays apart and it treats them the same, then maybe it is able to sort one of them, but there's no way it's able to sort both of them because the process needed to sort both of them is different, and that would be a contradiction. Okay, so that's how you could prove lemma A, although because I've said that now several times, and because I think it is actually a sort of natural property, we're going to leave it as being self-evident. Okay, lemma B. Since the number of leaves in the decision tree is n factorial, the height of the decision tree has to be at least log of n factorial. Okay, so lemma B we don't need to justify too much because that theorem we proved a minute ago actually gives us what we need. So the theorem simply says that if the number of leaves is n factorial, or if the number of leaves is k, then the height of the tree has to be at least log base 2 of k. So just plugging n factorial in for that gives us what we want. So the proof of lemma 2 is simply go look at the theorem from a minute ago. Okay, now we have lemma C, and that would be, that's going to be a little bit more involved. So lemma C is to assert, because I've mentioned n log n a couple of times, and I've also been talking about n factorial, and I suppose maybe it's become clear that I intend to claim that those two things are asymptotically equal, but I do need to prove that. That is a bit of a controversial claim. Now actually, to be clear, for the sake of the theorem I want to prove, the lower bound on comparison sorting, all I really have to prove here is a big omega. I have to prove that log of n factorial is larger than, in an asymptotic sense, it is greater than or equal to n log n. I'm actually going to prove the big theta because first, to prove big theta, I'll just prove big O and big omega. But the first reason I want to prove the big theta is that if I prove the big O side, that makes it a lot easier, I think, to digest the big omega proof, which is a little bit more complicated. And also, because log of n factorial is a sort of weird thing, it's sort of, I don't know, it's a fun idea, for lack of a better term, to play with it a bit, to sort of see what we can prove about it and to get some experience fiddling around with logarithms stuff. And it's true that in previous lectures, I don't know whether I'm some kind of weird like logarithm skeptic or something, but I often get a bit, I don't want to say annoyed or whatever, but I often find it to be a bit not unintuitive when proofs involve weird logarithmic identities, even though most of the time it is just the law of logarithms in disguise. I tend to feel like that is something that may not occur to most people as an obvious thing. So it's good to get practice working with it because logarithms do show up a lot, as we know because our analysis of recursive algorithms has shown us that logarithms tend to pop up a lot in the type of recursive algorithms that we write. So if nothing else, this is good practice for that. So to prove that log of n factorial is big theta of n log n, I'm just going to prove that it's both big O and big omega, and we know that that's sufficient to do the trick. Both parts of the proof use this sort of interesting transformation you can apply that uses the law of logarithms. So log of n factorial, well, I mean, if I expand out n factorial, that would be log of 1 times 2 times 3 up to n. And I observe that I have this big product, and the law of logarithms lets us take apart products and make them into sums of individual logarithms. So log of the product 1 times 2 times 3 up to n is equal to the sum of log 1 plus log 2 all the way up to log n. So it's this sum here. Although in the proof, I'm actually just going to leave the sum expanded all the way out like this because I intend to use a sort of clever trick in both parts of the proof that's easier to see if we write out each term explicitly. Okay, so I'm going to begin by proving that log base 2 of n factorial is big O of n log n. So this side of the proof is a bit shorter. What I do is I say, well, log of n factorial is equal to this sum. So log 1 plus log 2 all the way up to log n. Notice that the sum has n terms. And what I do is I observe that each of these n terms is less than or equal to log n. So I just say, well, then the whole series, the whole sum of all of these terms is less than or equal to the same sum, but with every term adjusted to be log n. So log 1 plus log 2 plus log 3 up to log n is less than or equal to log n plus log n plus log n plus log n all the way up to log n. And there are still n terms, and that's just equal to n log n. And we're done, because we've managed to show, using the regular inequality symbol, that log of n factorial is less than n log n, and therefore we have big O for free, I guess. What's interesting about this is, I guess intuitively at least, when the proof is this easy, like that is when you're able to sacrifice so much, like I turned a log 1 into a log n, that's a pretty big deal. It almost feels like that's telling you that log n factorial is quite a bit less than n log n. And there are reasons to sort of think about that. It just turns out, actually, that asymptotically they are still equal. It is a hint, though, that the other direction might be a little bit more difficult. But it actually does use the same sort of trick. Okay, so it's going to be over 2 pages, though, because it's a decent amount of algebra. Although it turns out an earlier version of these slides was only 1 page. I added more algebra than I think I need just to make this absolutely clear, because it is a rather unusual application of a technique. But there are ways to turn this into an exam question, so better to have more detail than less. So what we're going to do first is, on page 1, we're just going to show that log of n factorial is greater than or equal to this thing here. And for most purposes, this actually would be enough to say, because it is generally okay in this course, although if the exam says otherwise, then it isn't. It's generally okay to say this is pretty clearly big omega of n log n, and we'd be done. But on page 2, I will talk about how we could officially establish that this thing is big omega of n log n. Okay, so first I want to show that log of n factorial is greater than or equal to n over 2 times log of n over 2. And again, I observe log of n factorial is equal to log of 1 plus log of 2 plus some stuff plus all the way up to log of n. And that there are a total of n terms in this sequence. And that means the whole sequence, because every term in it is positive, is greater than or equal to if I just chop off the first half of the sequence. Now actually, I made a mistake a minute ago. Not every term is positive. We could have terms that are 0. Every term is non-negative. So the whole sequence is greater than or equal to just the second half of the sequence. So the second half of the sequence is if I just start at n over 2 and I just ignore everything before it. And that's obviously going to be smaller than what I started with. Okay, now connoisseurs will note that maybe n is an odd number, and therefore I should be using floor functions here. Okay, look, I know you're cool. I know you're going to be cool with this. So as long as we're all we just relax and take it easy, then we don't need floor functions. Yes, it's true. Theoretically, I should be thinking about what happens with floor functions. You're welcome as an exercise to go in and add all the floor functions, and you will discover the proof holds up perfectly either way. Because if I add a floor function, really, it doesn't change anything about the algebra I'm doing, and actually it would just make the sum a little bit bigger or a little bit smaller, but not by an asymptotic amount. Okay, so anyway, we're just going to say n over 2 to make our lives easier and to avoid overloading my LaTeX compiler with too many floor functions. So anyway, I managed to take this full sum, I just chopped off the first half of it, and it's greater than or equal to log of n over 2 plus log of n over 2 plus 1, all the way up to log of n minus 1 plus log n. And then I observe every single term in this sequence is greater than or equal to log of n over 2. So each term individually is greater than or equal to log of n over 2, which means the entire sequence is greater than or equal to what would happen if I just slam each term down to log of n over 2. And so this is sort of the same trick as I used on the previous case. And then I say, well, there are n over 2 of these terms, and they're each equal to log of n over 2. That's n over 2 times log of n over 2. Okay, so log of n factorial is greater than or equal to n over 2 times log of n over 2. Now the question is, and this is a bit pedantic, this next bit, but just in case we needed formal justification, how do I know that this thing is big omega of n log n? It's pretty clear that I can throw away the factor of 1/2, that coefficient at the beginning. Why am I allowed to get rid of the over 2 here? Okay, so now we'll show that n over 2 log n over 2 is big omega of n log n. Okay, so if I use the law of logarithms, I can show that this whole thing is actually equal to this. So what I'm doing is peeling off a log 2 term, or n over 2 times log 2. So it's equal to this, just by the law of logarithms. And then I observe that as long as, so then I say, I just break this log of n over 2 in half. So I say, okay, n over 2 times log n is equal to n over 4 times log n plus n over 4 times log n, and then the minus n over 2 just gets brought down here. And basically all I have to observe now is that as long as this term is at least as big as this term, this whole thing can be ignored. They cancel each other out as far as the greater than or equal to sign is concerned. So this whole thing here is greater than or equal to this as long as this term is bigger than the term at the end. And that happens as long as n is greater than 4. So when n is equal to 4, this log 2 of n is equal to 2, and 2 times n over 4 is just n over 2. So when n is greater than 4, this is greater than this, and that means that I can just sort of ignore them if I'm caring about a lower bound. All right, so now I've shown that n over 2 times log of n over 2 is greater than or equal to n over 4 as long as n is greater than 4. So if I take c to equal 1/4 and n naught to equal 4, I now have this is greater than or equal to c times n to the log base 2 of n for all n greater than n naught. Actually, I could have chosen c to be 1 over 2 there, but whatever. I mean, it works either way. So I've now shown by connecting this with the previous slide where I showed that log of n factorial is greater than or equal to this, that log of n factorial is big omega of n log n. Okay. Or actually, this should sort of, I guess I repeated myself there. Fair enough. Now, I want to prove my actual theorem. I want to state the lower bound on comparison-based sorting. And all I'm going to do here is just combine together my lemmas A, B, C, and D. Okay, so by lemma A, the decision tree needs to have n factorial leaves. By lemma B, that means the height of the decision tree must be log of n factorial. And to emphasize, because any use of a comparison sorting algorithm corresponds to a path from the root to a leaf of the decision tree, that means that if the height of the decision tree is log of n factorial, there have to be some inputs out there, not necessarily all of them, but some inputs out there that require log n factorial operations because they take me all the way to the bottom of the decision tree. They could require a lot of other work too. As I keep saying, just because the decision tree has height h doesn't mean the comparison sorting algorithm doesn't also do some other stuff on the side besides the comparisons, but it needs to do at least log of n factorial comparisons. And each comparison requires presumably at least one unit of time, which means at least log of n factorial operations are being performed. And then finally, by lemma C, log of n factorial is big theta of n log n, which means any comparison sorting algorithm needs to perform a minimum of n log n operations asymptotically in the worst case. Not on every input, but on at least one input. And that means no matter what comparison sorting algorithm you design, as long as it's comparison sorting and the only way it can learn about its input is via comparisons, it doesn't matter if you design it now or in a million years, it will always require big theta of n log n time in the worst case. And so it is, big omega of n log n time in the worst case. And that means it is impossible to create a sorting algorithm that is asymptotically faster than n log n. Now, that is our main result, and that's a huge deal. And that result deserves to be just the end of a lecture. That could be a lecture unto itself, and it almost is. But since we've been talking about decision trees, and they're not going to come up again, frankly, or they're only going to come up sort of in parentheses, I thought I would talk about a couple of other things. So this particular form of analysis, on the surface, it appears like maybe we could take it and apply it to a couple of other problems. And the answer is yes, but it turns out that those problems don't really need that result as much. Like there are easier ways of proving better lower bounds for them. And I also do want to spend a bit of time talking about the decision trees for real sorting algorithms, just because there's some interesting data to be analyzed there. Okay, so I could use the same trick, which is to figure out how many leaves the decision tree has and then bound the height of the decision tree to state a lower bound for a bunch of other problems. The problem is when I do this, it doesn't really result in a good lower bound because we've already found better lower bounds. So I could do it for a search problem, like linear search or searching in an unsorted array. If my search problem is supposed to return the index at which it finds the element I'm searching for, like my linear search function did earlier, then there are n plus 1 outcomes on an array of size n. There are the n indices of the array plus the one outcome where the thing isn't found. That means the height of the decision tree, if it's done with a comparison-based framework, is log of n plus 1, which is more or less log n asymptotically. Which means that any search problem, to solve any array search problem, we have to be able we cannot solve it faster than log n time asymptotically. This is a sort of boring result because we already know that if the array is unsorted, we need to do at least big theta of n operations. And so that's obviously much more than big omega of log n. And so it's not that exciting a result. Although this does sort of tell us that we can't do better than binary search. So binary search is log n, and this is telling us that there is no algorithm that is asymptotically faster than binary search for solving any variant of an array search problem. And so I guess it's useful in that sense. Okay, so here is our comparison sorting bound. That is a big deal. It's an important result. We can also prove, using the same idea, that the selection problem, so from 2 lectures ago, that the selection problem is log n. Because if I'm selecting the kth largest element from an n element sequence, well, any of those elements, if you give me some unsorted sequence, I have no idea which element is the kth largest, but all of them could be the kth largest element, so there are n possible outcomes. And that means at least log n comparisons are going to be needed to figure out which one is the kth largest. Okay, this is not very helpful because we already know that the selection problem does require big omega of n time, because we have to look at every element of the sequence to know which one is the kth largest. So this bound, you could prove a bound like this, but it doesn't really tell us anything. But those are just examples of how I could apply the same methodology to other decision-based problems. It's useful to know about those mostly because maybe at some point in the future you encounter a decision process and you just want some context because you might want to use similar logic to our sorting bound to prove that the decision process requires a certain number of operations at minimum. So maybe these provide context on how I might generally use it. You determine the number of outcomes of the problem, and then log of that number is the minimum number of comparisons needed if the only way of distinguishing between elements of your input is by making comparisons. So there's that, although neither of the two new things on this slide are very profound. They are ways of applying the same logic. Now finally, I want to talk about decision trees a bit more as a way of maybe understanding and sort of circling back around to the way that we analyze sorting algorithms, as sort of a way of seeing from a different point of view some of the same things we observed while analyzing algorithms asymptotically using the pseudocode. So here is a decision tree for the 4-element case for merge sort. Well, for my merge sort implementation. So you could write a different implementation and it might have a different decision tree. I believe my implementation was competently written. This is actually data I collected as part of a research project in, I think, like 2014. And so although it's old, it's not a timing experiment. So I could run it again today and it would have the same sequence of comparisons. It would hopefully take less time because it turns out the experiment was large enough that it took quite a while. So there are 24 permutations of the different 4-element arrays up to the identities of the elements themselves. So there are 24 different arrangements of 4 elements. And notice that in the decision tree for merge sort, the tree is pretty compact. That is, I have no redundant comparisons, and that all of the leaves are at depth 4 or 5. So they're all below this line here. And that sort of makes sense because the number of comparisons performed by merge sort is very consistent. The best case of merge sort is n log n, just like the worst case. And so it makes sense that the leaves are clustered pretty tightly at 1 or maybe 2 different depths of the tree. On the other hand, if I look at an implementation of selection sort for arrays of size 4, not only is the tree taller, but you'll see that it's full of these weird sort of stringy appendages where it's performing irrelevant comparisons. And there's a bunch of them. So let's see if I can find more. There's one over here, and there's one also there. There's another redundant comparison there. And that's the result of selection sort asking questions that it already knows the answer to. And we saw before that when we analyzed selection sort, that selection sort does exactly the same thing on every single array. I mean, obviously, which minimum it finds at each step is different, but it performs the same sequence of comparisons on every array. Every case is the same. There is no best case or worst case. There's just one case of selection sort. So as a result, selection sort is performing a bunch of comparisons that it should know better than to perform. It's wasting a bunch of time on useless comparisons. And because it performs the same sequence of comparisons for every single array, every single leaf ends up at the lowest depth of the tree because it is doing the same amount of work for every single input. And that means that every single leaf is at the same place. And of course, that illustrates that selection sort is a bit inefficient. Not only the redundant comparisons, but the fact that if I didn't ask any of these questions, I could put this leaf all the way up there and just come to the right answer pretty quick. Now we take a look at quicksort. And although we're only looking at the tree for height 4, or the tree for 4 inputs, which doesn't tell us a lot, if we could look at the quicksort, at the decision tree for quicksort for like 100 inputs, this pattern would be exaggerated, but we can already begin to see some of the personality of quicksort showing through. Speaking of which, it makes sense that merge sort is a very methodical algorithm that's very well organized and compact, but as a result, every input takes about the same amount of time. It's very efficient because no time is wasted, but every input, the running time is sort of shared evenly among all cases. Versus selection sort, which is sort of oblivious. Selection sort doesn't really pay much attention and therefore does a bunch of useless work, but it is also very methodical, and so every input takes the same amount of time. The personality of quicksort is a bit more like laissez-faire, I guess, for lack of a better term. Some inputs are sitting all the way down at depth 6, which makes sense because we already know that quicksort has these worst cases where it does a bit more work than merge sort might do. On the other hand, some inputs are higher up. And this continues. If we keep making bigger and bigger trees for the larger input sizes, we begin to see this issue increases. That is, the depths of leaves in the tree for quicksort are very different over time because quicksort has all these different patterns that can arise due to the choice of pivot. So the leaves have depths ranging from 4 to 6. Although, to be clear, in this example, depth 4 isn't any better than merge sort. Merge sort's leaves were at depths 4 and 5. The experiment I was referring to from 2014 didn't just work with trees of where we talked about input size 4, because that wouldn't take too long to repeat. I actually went all the way up to input size 15, and if you look up the value of 15 factorial, you'd understand that it's not the kind of experiment I could have rerun over lunch on the way to record this lecture. So it's a large number. And so what I did was, for these 4 algorithms, for selection sort, merge sort, quicksort, and there's this handsome stranger again, we're going to have to meet heap sort soon enough, but not quite yet. That we can see that the maximum depth of the leaf, so the maximum number of comparisons required in the tree for each algorithm, and the average depth of a leaf. In other words, the average number of comparisons required. And we notice, so one very stark thing is that for selection sort, actually I should talk about the experiment methodology. So to evaluate this, because I observed earlier that the exact values of elements don't make much of a difference, it's the relative ordering of elements, it's sufficient to simply talk about all 15 factorial arrangements of the values 1 through n, and just look at the tree that we produce by trying to sort every possible arrangement of values. And to be clear, this was an empirical experiment, so I didn't deduce these things theoretically. I actually ran the algorithm on every single one of these permutations of 1 to n and just counted how many comparisons it performed and in what order. And that's how I got this data. That's why it took so long. And so remember that means that this is subject to the way that my implementation of merge sort and my implementation of quicksort worked. Although, as I said, I believe it was done properly. So if you wrote it, it might be plus or minus a couple, but I think that the trends would be pretty much the same. Okay, so one really stark thing that jumps out at you once you notice it is the average number of comparisons performed by selection sort is equal to the maximum, which means literally that the number of comparisons performed is identical on every single input. No matter what array you give selection sort, it does the same number of comparisons. What's even more strange and sort of weird almost is that this number is exactly equal to n times n minus 1 over 2. And you can try that out. Try it out for 15 or 14. It's going to be 105 for 15. 15 times 14 all over 2. And what's really strange about that is, recall when we analyzed quicksort, we came upon this familiar sum, 1 plus 2 plus 3 plus up to n minus 1. And it turns out that it does literally that exact number of comparisons. The number of comparisons is exactly equal to the number of iterations of that inner loop of selection sort in the worst case, or actually in every case for selection sort. So interesting, selection sort is actually pretty much as inefficient as one can get for an n-squared sorting algorithm. Now for quicksort is a different story. For quicksort, the average number of comparisons is pretty good. It's competitive with merge sort. But the worst case, so the maximum number, is the same as selection sort. So for that worst case input, let's say when the array is already sorted if the pivot is the first element, quicksort will indeed perform an identical number of comparisons to selection sort. And that is a really stark indicator of the worst case of quicksort. We already know from our theoretical analysis that quicksort's worst case is n squared. Well, if you're skeptical about that, or if you don't quite buy this, that the theoretical analysis maps onto real life, here's your evidence. This is actually quicksort doing a big O of n or big theta of n squared operations on particular inputs. And it works out precisely to be equal to this maximum value we computed for selection sort, n times n minus 1 over 2. If you need any more evidence that asymptotic analysis is relevant to talking about rates of growth of algorithms and that our analysis technique was reasonable, here it is. We actually can see in practice, if we measure the number of comparisons, it does seem to map on to what we already derived asymptotically by our other analysis technique. And that's just the number of comparisons. So quicksort and merge sort and selection sort do all sorts of other work, and heap sort. They do all sorts of other work besides comparisons, but just the number of comparisons ends up being big theta of n squared for quicksort in the worst case. Speaking of which, notice how it says that it's competitive with merge sort. So actually, merge sort seems to be quite reliably performing fewer comparisons than quicksort. But we did observe when we talked about quicksort and merge sort that on average, quicksort is a bit faster than merge sort in practice, like in a timing experiment, for example. So what gives? And there is actually a pretty simple explanation, which is that just because quicksort does more comparisons doesn't mean that quicksort is slower overall. I mean, it doing n squared comparisons means that it has to require big theta of n squared time. But if it does maybe 2 or 3 more comparisons, remember that the full running time of the algorithm is a combination of the number of comparisons and a bunch of other factors as well. And merge sort does have to do quite a bit of extra bookkeeping. It has to split the array, then it has to do that shuffling merge procedure that involves a lot of fiddling around with elements, whereas quicksort has a very simple split procedure, and the merge procedure can often be trivial. And so in that case, what we're observing here is basically that quicksort does a competitive number of comparisons and manages to get an edge in some other part of the algorithm, so in the number of copies or swaps that it's doing. And that might be the reason that quicksort tends to be faster in practice. But this does demonstrate that quicksort's overall average performance is pretty decent, at least up to n equals 15. Of course, we can't generalize just by looking at numbers how it would apply beyond then. But there is enough data here to sort of support the trends we've already derived theoretically that apply for any value of n. So this is matching up with our expectation of how things work. I can't really tell you very much about heap sort, and I mean that one's on me, sort of. What I will observe, though, is notice how heap sort does seem to perform quite a few more comparisons than either merge sort or quicksort. And there is a good reason for that, but the number of comparisons is growing according to a function of n log n, so some multiple of n log n. So heap sort is an n log n algorithm, but it does seem to have quite a bit more overhead. It does seem to need more comparisons. It does have other advantages, though. And when the time comes, we will see what those advantages are, to the point that there are standard libraries out there that do use heap sort as their standard sorting algorithm, or as one part of their standard sorting algorithm. So we shouldn't write heap sort off, just because heap sort does seem to require more operations, and yes, in practice, it does require more overhead, unless you're very careful. You can reduce the overhead in certain ways, but it can be quite expensive. That doesn't mean it's not n log n. Asymptotically, it's still n log n, and so it's still one of the big three, although, to be honest, if you're up to me, quicksort wouldn't be considered one of the big three. I think that the best, the most elegant, and the optimal sorting algorithm should just be merge sort. It's n log n, it's a very streamlined, clean n log n, and heap sort also should get some credit, but yeah, heap sort does have a bit of extra overhead, versus quicksort that, to be honest, I'm not that big of a fan of at all, and I've said that a few times in the past as well. All right, so where does that leave us? Now we know that no matter what comparison sorting algorithm we're talking about, even one that hasn't been invented yet, we need at least n log n time for it in the worst case. So while there's still room for there to be better sorting algorithms out there, maybe in the best case or in an average case they're better than merge sort or quicksort, we now know that we can't break the n log n barrier, not with any algorithm that exists now, not with any algorithm that will ever exist within a comparison sorting framework. Of course, non-comparison based algorithms can break this boundary all they want, because the comparison sorting bound only applies to comparison sorting algorithms. And that's why we already saw, in certain cases, you can sort n things in linear time with radix sort. Nothing about that contradicts the bound that we proved today. So I suppose, after all I just said about heap sort, it is about damn time that I told you about heap sort. So I guess next up on the agenda is a discussion of a data structure called a heap, which will allow us finally to find out all about this mysterious stranger in our midst, heap sort.